what I want to cover is the transmission gate. Transmission gate circuits. Okay. So what is a typical 2:1 multiplexer logic function? If this is my select line A, B, Y equal to what? S bar A plus SB. Right? Now, if you want to implement this in static CMOS logic, right, you clearly have to, implement this AND of S bar into A plus S into B and invert it and all that stuff, right? Similarly, if I now take this to a 4:1 multiplexer, it's going to become that much more complex because it will be S1 bar, S0 bar into A, S1 bar, S1 into B, and so on. And as I take the complexity higher and higher and higher, the circuit is going to become really, really complex, right? So it turns out that when you want to implement something like a multiplexer, then the best thing to use is a transmission gate. Okay, so a transmission gate circuit is like this, right? So we obviously don't put only one NMOS or one PMOS because NMOS can only pass a 0, PMOS can only pass a 1. So to pass both logic levels, you put them in parallel. Whichever is least resistance will pass it easily, right? So this is the basic idea behind the multiplexer, transmission gate multiplexer, right? So if you look at this, this is S and this is S bar. Right? The key thing that we are exploiting here, right? I will leave it you to go and figure out how to implement the static CMOS version of, let's say, a 4:1 mux. You will see how complex it is, how many transistors you need, what the logical effort is, and so on, right? It's a big problem. The main thing that we are exploiting here is if a transmission gate is off, right, then the output goes to a high impedance state, right? I'm driving one end with an input A or B. But if that path is off, that means both the NMOS and PMOS are off, then the output, let me say Y1 and Y2, right? Y1 and Y2 will go into high impedance state in a mutually exclusive manner. And therefore, I can do Y equal to Y1 wire OR of Y2. This is what is really saving me plenty of gates, right? Because it goes into high impedance state, I can do wired OR connection, and now I can do a wired OR connection for any number of such transistors, transmission gates. For example, if I want to implement, let's say, 64:1 mux, right? What do I need to do? I basically need to simply do this. This is I1, right, or I0. We'll fill the select lines later. I1 all the way down to the 64th. I63, right? And I can simply wire OR all these connections and get my output Y, which is a 64:1 mux. Now, what are the select lines for this? So I need the decoder, which is going to decode a 6:2 circuit. Correct? So I put a decoder which gives me the following. Select line S0, S1, S5, and what I get here are my decoder signals D0, D1, D63. But in order to turn on this pass transistor, I need both true and complement outputs. I need the decoded output and the complement of the decoder output, because for the PMOS I need that, right? Therefore, I will basically make this as D0 bar. This is D1 bar. This is D63 and D63 bar. Okay, how do you implement a decoder? Well, that again cannot be done, just for example, if I want a 6 input NAND gate, AND gate, I cannot do it, right? Because for logical effort reasons. Therefore, you build this from smaller 3:8 decoders. You build 3:8 decoders, then use them, cascade them, and then build your 6:64 decoder, right? So, like I told you, this is a case where both two and complement outputs are needed from the decoder. So, typically here, if you want to, let's say, do a decoding and then a level translation, then CVSL is a natural choice because it also does level translation for you. Additionally, it also gives you this true and complement output that you need, that your decoder, that your multiplexer needs eventually. Okay. The only problem with this style of circuit is, if I ask you what is the drive strength of this multiplexer, what is the answer? What's the drive strength? If I have an inverter, unit inverter, then I say the drive strength is 1x, right? If I have a unit NAND gate, the drive strength is 1 again. We have sized it like that. Now, if I ask you what is the drive strength of this transmission gate based multiplexer, what is it? So clearly, that you cannot answer that question, because unless you tell me what is driving this gate, I cannot tell you what the drive strength of this gate is. For example, if I have an inverter here, right, or a buffer or whatever, if you don't want inversions, then put a buffer, no problem. Then I can now answer that question, because if I look at this inverter, right, if I look at this part of the circuit, it is going to be an inverter followed by a transmission gate. So if I open this up, right, and draw it at transistor level, this is my PMOS, NMOS, this is my transmission gate. Okay, this is my D0 bar. Now you can answer that question, because the PMOS is going to be pulled up like this, the NMOS is going to be pulled up like this, pulled down like this. So now I can even answer the question, what should the size of this PMOS transistor be, right, or the NMOS transistor be in this transmission gate. So if this is, let's say, 1 and 2, what should the transmission gate's size be? So again, what you have to do is, you have to just redraw this in a fashion that we already know. Okay, so what I'm going to do is, I'm going to right, this is my inverter's input, right? If I go back here, I'm just opening that up, opening this inverter up and fitting my transistors in there. My transmission gate, I'm putting it in there, okay, so that I get a stack, because that's what we are used to, right? So if this is my inverter's input A, then this will be A, right? And this is going to be my output Y. This will be D0 bar. Am I done? Is this equivalent to that earlier circuit? Huh? Why? Yeah, I have to short the other two terminals as well because it's a parallel thing, right? So I have to draw this also. Now I'll ask you the question, what should the sizes be? 2, 2, 4. So you would say this is 4, right? What about that 2 there? I mean, should that PMOS be 4? Technically, it's not necessary because the NMOS and PMOS are actually conducting together. Even though the NMOS cannot pass a logic 1 completely, for most of the time it's going to actually allow conduction. Until it goes to VDD minus VT, the NMOS is also going to conduct along with the PMOS. Therefore, the two resistances are in parallel for most of the time, and therefore you can slightly give an allowance, and typically they make this also 2. Slight deviation from what we have done because these two NMOS and PMOS are in parallel for both logic states. This is very important because when we do sequential circuits later, we will use this. Okay? Clear? Now it turns out that you really don't need to make this parallel connection. I can still get a very valid gate that does exactly the same functionality even if I remove this parallel connection here. Okay, so if I redraw that circuit, it's going to look like this. No, I need to make this separate. This is my input, enable bar. So now what is the truth table of this circuit? I'll do A, enable and Y, 0 0 0 1 1 0 1 1. What happens when enable is 0? Output is what? Yeah? Floating or high impedance state. When it is 0 1, yeah, when it is 0 1, when enable is basically 1, that gate basically is like an inverter. It just inverts the input A, right? So this is going to be 1 and this will be 0 and this will be Z. So not surprisingly, this is called a tri-state inverter. Okay, because like I told you, transmission gate, sometimes you need a gate driving it before, whereas the tri-state inverter is a complete gate by itself. I can use it anywhere, I can size it, I can be done with it. Whereas transmission gate, I have to be careful about where I place that gate and size it according to that circuit, right? But both effectively perform very similar functionalities. And here now the sizing should be what? 2 2. Now it should be 4 4. I have no choice because I don't have that parallel conduction, right? When it's going to logic 1, only PMOS will conduct. When it's going to logic 0, only NMOS will conduct. This is very critical, as you will see later. Okay, so you can use, again the output Y therefore of this circuit can be wired OR to some other tri-state inverter if you can ensure that they are mutually exclusive. That's the advantage of this kind of a circuit. Okay, clear? Any questions here? Yeah. Yeah, here, right? Yeah, so if you look at this circuit, even when I am passing logic 0, see in the tri-state inverter, when the output has to go low, the output only has to go like this. Only NMOS will conduct, PMOS is turned off. Now in my other case, because I have this parallel connection, this red parallel connection here, right? This red parallel connection here, both the NMOS and PMOS of the transmission gate will conduct together. Though the NMOS will be like slower, it will conduct only up to VDD minus VT. For most of the time, it is going to conduct. Right? So, in some sense, they are both in parallel and therefore you can reduce the size slightly. So, it is instead of 2244, you are able to make it 2224. That's all. Okay. Why not? Yeah, I think, yeah, see, this is not, okay, let me tell you, this is not like some, derivation where I can show that this is minimum. It's in practice that you typically do this. That's all. It's a reasonable thing. You have to figure out from simulation if maybe 1, 2 is also okay. But you have to figure out from simulation. That's all I'm saying.